Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this ongoing series in stereochemistry, we have begun looking at chirality. Last lecture we defined terms such as enantiomer, diastereomer, and chiral molecule. We're continuing with our look at chirality by examining the tests for chirality in molecules. Last lecture we learned that you could test for the chirality of a molecule by making models. Make a model of a molecule, build the model of its mirror image, and then test to see if they're superimposable. So we test to see if the models are superimposable. Now, if the molecular model is superimposable upon its mirror image, they're identical. But if they're non-superimposable mirror images and stereoisomers, then they are a pair of enantiomers. Now, as we close the last scribblecast lecture, I commented that it is important that we be able to do this type of testing utilizing two-dimensional drawings. If we have, for example, a molecule, we can represent its three-dimensionality, we learned, utilizing wedges and dashes. Wedges mean the structure is coming out of the board. Dashes means that the structure is going into the board. We learned that a molecule such as this has four different groups around it. A tetrahedral carbon is chiral and can exist as a pair of enantiomers. Now I can rotate this molecule and produce the same structure, the same molecule, just looking at it in a different perspective. If I rotate that way and then rotate a small amount that way, I can actually get this structure. Now you can actually build a model, and you can turn that model of this molecule such that the bromine and chlorine are coming out at you, and the H and the I on the vertical axis are going away from you. And so we represent this as the H and I going into the board with dashed bonds, and the bromine and chlorine coming out at you with wedged bonds. This is the exact same tetrahedral structure. It's just being viewed along a different alignment. Now, what's interesting is an individual took this shape and said, we will create a shorthand notation where the vertical line will always mean the two atoms are going away from you, and the horizontal line will be the two atoms coming out at you. The central intersection point will be your chiral carbon. This was a shorthand representation of the molecule drawn on the left, leaving out the wedges and dashes. It was understood that the bromine and chlorine had to have wedges, that the bromine and chlorine on the vertical line are always drawn so that they're coming out at you. If you do this for every chiral carbon, it will lead to eclipse groups when we look at molecules with more than one chiral center. The H and the I, the vertical axis, is known to be going away from you. This was called a Fischer projection. And the Fischer projection represented a method of drawing three-dimensional molecules in 2 dimensions. But in order for it to work, you have to remember the essential rules of the Fischer projection. And the 3 main rules that you have to know are, for Fischer projection, 1, the intersection is your chiral atom. Your intersection of the 2 lines, I'll have to rub that out as well. The intersection point of the 2 lines is your chiral carbon. The second rule is that the vertical line, represents groups going into the paper. Groups or atoms going into the paper, away from you. The horizontal line represents groups or atoms coming out of the paper. Okay. So those represent 3 main rules for the drawing of Fischer projections. Now there are some standard rules you will be given for drawing of standard Fischer projections, such as the longest carbon chain vertical, the highest priority group by nomenclature at the top of the chain. But just because you don't follow those rules doesn't mean you don't have a Fischer projection. These 3 rules, though, are exact and must be followed. I'm going to exemplify the other 2 rules by giving you a Fischer projection of another molecule. Let's consider this molecule. We have a carboxylic acid, and then we have a carbon hydrogen, and I will give it an OH group, and we have a CH3. Now, in this molecule, one could ask, are there any chiral carbons? Well, to be chiral, you must have 4 different groups, and a C double bond cannot have 4 different groups around it, so C double bond O is not chiral. The CH3 has 3 hydrogens, so it again is not chiral. The central carbon has a carboxylic acid off of it, a methyl, an H, and a hydroxyl. It is chiral. So this is our chiral carbon. That's a chiral carbon. Now, the chirality is not shown here. In other words, I have drawn it without showing any of the shape in 3 dimensions. I could draw this structure like this, just as we drew our previous molecule. So here is a molecule, a three-dimensional representation of the above molecule where I'm actually showing the chirality, I'm showing you the dimensionality, and I've drawn a specific enantiomer. Now, one of the common rules in Fischer projections that's commonly employed is draw the longest carbon chain vertical. Now, it doesn't mean you don't have a Fischer if you don't follow this rule. But this might be viewed, if you like, as the standard orientation of Fischer's drawn. So you will notice on questions on tests, I often employ this in the question. And so you must draw what you're asked to draw. Okay. Now the longest carbon chain, obviously, is the CH3, C double bond O. So if I was drawing a Fischer, and I put the longest carbon chain vertical, I would be placing the CH3, C double bond O, OH vertical. The question is which one's at the top. The other convention is typically the highest priority group by nomenclature is placed at the top, the highest priority group of the carbon chain. So, you know, we often place the highest priority group at the top. Okay. So the highest priority group at the top. If you do this, the highest priority group between the methyl carboxylic acid is the carboxylic acid. So the CO2H will be put at the top and the methyl's at the bottom. Now, you will be allowed to bring in your quiz a single chirocarbon with 4 different colored bonds on it. And the reason you'll be allowed to do this is to help you determine the orientation in which to draw your Fischers. You see, this CO2HCH3 is going away from you. It's a specific orientation. And because of that, this locks the H and OH into a certain position. So if you are actually rotating this 3D so that you're getting this, how does the OH and the H have to align? Well, if I'm actually turning this guy sort of along that axis to get these going away from me, this OH will swing to this side. Now, you can do that in a model. What I suggest you do is you actually build a model with different colored bonds, hold those bonds in this orientation so the OH is coming out, you can write down the color for each, and then turn it so that the colors go this way, that the CH3 and CO2H are going away from you. And ask yourself, where does the OH, the colored bond that represents the OH, where does it end up? On the right or the left? And so the Fischer projection for this molecule, following longest carbon chain vertical and highest priority group at the top, would be that. Now, the reason we've learned to draw Fischer projections following a fixed convention, a set of rules, is that it allows us to determine if 2 Fischers are the same molecule, that is the superimposable, or they are a pair of enantiomers, that is the non-superimposable. And Fischers can be drawn in a wide range of orientations following the first 3 rules on the previous screen. These 2 rules are optional. They allow me to make everyone draw the same thing on a test, but makes it easier to mark. But you can draw fissures, you know, an appropriate fissure of this molecule, an acceptable fissure, could be, for example, or at least an appropriate fissure for this molecule. Could be something like this. Now certainly this represents a Fischer projection. I mean, the vertical line's going away from you, the horizontal line's coming out at you, and the C represents a chiral carbon. It's just not drawn by these two standard conventions. And so while this represents one of the two possible enantiomers for this chiral center, the question is, does it match A? Is it the same as structure A, the same molecule, just looking at it from a different angle? Or is it the mirror image enantiomer? And it would be really nice if there was a simple way in which to check that out, to see if this molecule I've just drawn is the same or the enantiomer. And there is a fairly simple way. How this works is what we're going to do is we're going to start switching two groups. We're going to switch any two groups and count the number of times we do a switch. Our target is to turn this molecule right here, this molecule, our target is to turn it into structure A. Now we're only allowed to switch two groups at a time. So I draw an arrow and I'm going to switch any two groups to get me closer than that. And I can see that what will get me closer to this is actually getting the OH to the right. So I'm going to switch the H and the OH. So this will still be CH3. And then I'm going to, oops, I switched it. So this becomes an OH. So I switch the H and the OH and I get this structure. And I just keep on switching any old way I want to. So for now, I see if I get the CO2H at the top. So I'm going to switch that. Did I have to do it that way, that order first? No, you could have done the switches anyway. Now I'm getting really close. I have the CH3 here. And I've got the H at the bottom. That just leaves one more switch. If I switch the H and the CH3, that'll get me to the original structure. Now, all you got to do is count up the total number of interchanges or switches. How many interchanges did you have? Well, I had to switch to get the original structure. I had to switch once, twice, 3 times. I had to do 3 switches. Now, if to get to the original structure, you do an even number of, I call them interchanges, or the switches, the same thing. Interchanges. Then you are the same or identical. You're identical if you do an even number of interchanges. But if you do an odd number of interchanges, you are enantiomers. You've made the enantiomer. Well, we said we did 3. We did 3. 3 is an odd number. That means this structure right here, our original structure is the enantiomer of A. Now you might say, oh, it doesn't look like a mirror image. Well, that's just because of the orientation you're looking at. Remember, if you make a three-dimensional model, put the 4 colored bonds around the tetrahedral carbon and look at it, you can turn this at all angles when you're looking at it. You don't have to be looking at it in a way that makes it look exactly like the mirror image. With this rule, Fischer projections become really powerful, because now on a test, you can be asked, very easily, you can be asked to show your work. Show how you selected that these two molecules were the same or different. And you could be asked, you'd have to draw each interchange, then count up the interchanges, state it's an odd number, and then state, therefore, structure B is the enantiomer of A. All right. So there's lots of examples, questions you can try to do this. And we're going to be pursuing this later, continuing with this as we take a look at the nomenclature. But before we do, we have to talk about one more aspect or property of enantiomers, molecules that are chiral. And that is how they differ. You see, enantiomers are almost totally identical. In terms of chemical properties, they are identical. In virtually every way. With regards to melting points, they're identical. Boiling points, identical. Solubilities, identical. Refractive indices, identical. Almost all physical and chemical properties are the same. Only two properties are different. Enantiomers differ in their interactions with other chiral molecules. Now, you're really far more familiar with this definition than you might think. And the analogy of the hand comes to light once again. See, your hands are identical with regards to grabbing things up. You may be left-handed, right-handed, but if you're picking up a hammer, or a screwdriver, or the mouse for a computer, they function the same way. But one could argue that in the simplistic sense for this analogy, those structures are simply not chiral. They may be, they may not be, but for the simplicity of this analogy, you're dealing with interactions with achiral units, units that are not left-handed, right-handed. But when you try to use your hand to shake someone else's hand, you have to use the appropriate hand. The reason is the left hand interacts differently than the right hand with other hands or other chiral molecules. So when someone puts out the right hand, you have to put out your right hand to shake hands with them. If you put out your left hand as someone's putting out the right hand, you're going to have a hard time trying to shake hands. And so it makes sense by that analogy that enantiomers would have some differences in how they interact with other chiral molecules. And we'll talk more about that one later. The next difference has no simple analogy, and that is how the enantiomers interact with plane-polarized light. Now to understand, and this is what we're going to focus on next, how these chiral molecules interact with plane polarized light. Now in order to explain this, we have to understand some basic behavior about light. Now light travels in waves. Light is referred to as an electromagnetic phenomenon because light consists of two perpendicular oscillating fields. A light beam consists of, I'll try to draw this as best I can, what may be called the electric field. So I'm going to put blue pointing up as the electric field. And I'm going to draw in red the perpendicular magnetic field. Red will be the magnetic field. And these two fields are perpendicular. And they are represented by oscillating waves. And we're going to represent the general direction of propagation. So the beam of light is traveling in this direction. Okay, so I'm going to draw in now my electric field. I'll try. Oh man, come on. Try to make this as neat as possible. Okay, and I'm going to draw in the perpendicular magnetic field as best I can. Have to try and draw it at an angle. Try and get this. So, try to draw it flat there. Now, suppose you were able to be looking at this beam of light with your eye. That's supposed to be an eye. Okay, there. So you're looking at this. What would you see in ordinary light? Well, in ordinary light beams, if you could actually just focus, say, on one of these oscillations, say we're going to just look at the electric field, the oscillations would occur randomly. There'd be oscillations that are vertical, oscillations that are diagonal. You'd see a whole series of electric field oscillations as you looked at the light. The light is said to be oscillating in all possible planes. But we can pass this light through a filter. The filter is called a polarizer. The polarizing filter is designed to block out all electric field oscillations except those in one plane. So when the light passes through and it emerges, the beam of light is oscillating one plane because that's the only light that can pass through this material. And because the electric field is now oscillating in one plane, the light is said to be plane polarized light. Or PPL for short, if you like. Plane polarized light. So we can define plane polarized light. Plane polarized light, and you should record this, is light in which all wave vibrations have been filtered out except those in one plane. Plane polarized light is light in which all wave vibrations have been filtered out except those in one plane. Okay, well, what's so special about that? Well, suppose I take my plane polarized light and I fire it at a container. And inside this container is a solution. And these little blue dots that I'm putting in this solution are chiral molecules of a single enantiomer. Okay. As the light passes through the solution, the light may be rotated to the right or to the left. I'm going to rotate it to the right. So from the original oscillation, the light has been rotated by an angle of this many degrees. Okay? That much angle of rotation, because that light beam passes through. Now this change of rotation of plane polarized light is caused by the interaction of the light with the electron clouds of the bonds of the atoms in the molecule. Now, since plane polarized light is rotated thusly, we can define some more terms. Optical rotation, for example. Optical rotation is the rotation of plane polarized light. Now, I expect you to write it out, plane polarized light, but to save time, I'm going to start using PPL for plane polarized light. You shouldn't do that, but you should write it out. Plane polarized light, that occurs when passed through a solution of a single enantiomer. So this rotation that we measured in degrees is called optical rotation. In conjunction with optical rotation is the term optically active compound. Optically active compound. Optically active compounds are compounds that rotate. The compounds that rotate plane polarized light. And I'm going to put P, P, L. I would please ask you not to use this abbreviation on tests. Optically active compounds are sometimes also called optical isomers. Now, since we're dealing with chiral compounds, I said optical rotation is rotation caused by a single enantiomer, solution of a single enantiomer. Does that mean all chiral compounds are optically active? Be careful. You're optically active or you're an optical isomer if you rotate light. If for some reason there is an enantiomer that has zero rotation, then it would be optically inactive. It would not be optically active. And you wouldn't use that term. All right. Because of this, as you can imagine, and because of these definitions, it becomes important to be able to measure this angle of rotation. In order to do that, we need a device that can actually measure the rotation of plane polarized light. Well, how would this device work? Well, the device would consist of a light source. So we've got a light bulb here. And in this light bulb we have an element. The common source of light is the sodium lamp, and we actually use the D line. So we often use the sodium D line for our source of light in optical rotation experiments. Now, remember, the light coming from this will not be polarized. It will have oscillations in all directions. Okay? Let's try and make that a little bigger if we can. There we go. So the oscillations will be in all directions. Now what we do is we pass this through a polarizer or a polarizing filter. So that the light is now oscillated. The light is now oscillated. The light is now oscillating in one plane. Now on the other side of the polarizer is our sample tube. And our sample tube is that which the beam passes through, and it will have a solution, and inside that solution will be dissolved our chiral molecules. Now we need to know a couple things from this when we actually do these measurements. One, you must know the concentration. And the concentration in this device is given in grams per mil. So we express concentration in grams per mil. We should also know the length of the tube. The length of the tube is called the path length because it's the path the light travels. So the path length. And that is measured in decimeters, I believe. Yes, in decimeters, dm. Okay, now the light is going to emerge after it's gone through a polarized. So let's say it hits the solution oscillating straight up and down. Okay, and then it's going to emerge from here, rotated. So I'm going to rotate it to the right a bit. So originally it was straight up and down, and now it's rotated this much. But now we need to be able to determine that. And this is done with a second polarizer. Now the second polarizer is actually called the analyzer. It's called the analyzer. Now the analyzer is a polarizing filter that we can rotate. You see, what we do first is we don't put any chiral molecules in. We just put the solution. And so when the light goes through, it won't rotate. And we turn this polarizer so that the light gets completely blocked. And we can measure that as our zero position. Darkest point. No light is coming through. And we can actually look at that with our eye. Then we put molecules in the solution of known concentration. We know the tube path length. And we pass it through, and the light rotates this time. And we've marked on our filter where it was the darkest point. You could equally mark the brightest point as well. And then you turn to the same effect again. But this time the polarizer will turn to a new position to block completely the light of the rotated angle. And this polarizer's new angle of rotation can be measured. And so, utilizing a polarizing filter, which we call the analyzer, and doing two measurements, one with no chiral compound in and one with chiral compound in, we can actually determine the degrees of rotation for our concentration and our path length. And you should know those two variables are important because the amount of rotation you're going to get in this system depends on how many molecules it hits. And how many molecules the light beam hits as it's traveling through depends on the concentration. And the longer the tube is, the more the light is going to run into molecules. The more rotation you get. So those two variables affect how much the light's going to rotate. Now this device is called a polarimeter. A polarimeter is designed to measure the amount of rotation caused by a solution of a specific enantiomer upon plane polarized light. Now you can immediately see a problem with this setup, and that is, well, what happens if one group researching a compound has a path tube that is 2 decimeters long, and they decide to use concentrations of 5 grams per mil, and another research group in another part of the world use 1 gram per mil and use tubes of path length 10 decimeters. The amount of rotation for the same enantiomer will be different because they have different concentrations and different path lengths. So even though observed rotations may differ, Measurements taken with a polarimeter could be converted to a standard observed rotation. Now, before we define what the standard observed rotation is, I just want to reiterate what you have to be able to give me in order to properly describe the structure of a polarimeter. What you need to properly build a polarimeter is a light source, your polarizing filter, which is called the polarizer, then your sample tube, and emerging from the sample tube we have another polarizing filter called the analyzer. And the analyzer has a degree scale that allows the rotation to be measured. And remember that two measurements are always taken. One, you must zero the device utilizing solution with no enantiomer, and then you measure the rotation afterwards. All right. So how do we handle the fact that we may get out different observed rotations, given the fact that not everybody's going to use the same concentration and not everyone's going to use the same path length or length of tube? Well, chemists have defined a term called specific rotation. And specific rotation is an arbitrary standard by which all rotations are reported. It's defined as the amount, okay, I'll use a short form for amount of rotation that would be caused, so caused by 1.00 grams. 1.0 grams of sample, compound, or enantiomer. In 1.00 mils of solvent. In a tube with a path length path length of 1.00 decimeters. Now, a decimeter, remember, is a tenth of a meter or 10 centimeters. So we're going to let the rotation in degrees that different groups see be symbolized by alpha. Now, alpha is our observed rotation. Alpha equals the observed rotation in degrees. So specific rotation, which we've just defined, I'm going to symbolize by an alpha in square brackets. Now, when specific rotations are reported, you often see a number as superscript, such as this, and a letter, often D. The number refers to the temperature at which the measurements were taken, and the D stands for the source of light, if you use the sodium D line. And the reason for this is you can get subtle variations with temperature and different wavelengths of light. But specific rotation is given the symbol. Now, in order to convert an observed rotation into specific rotation, I need only divide by the length, L, and the concentration. So L times C. So alpha is over L times C, where L equals the length of your tube in decimeters. It must be in decimeters. And C is your concentration in grams per milliliter. Utilizing this formula, any observed rotation can be immediately converted to a standard specific rotation. In other words, for a single enantiomer, the specific rotation is a constant and never changes. Okay, so specific rotation is a constant for an enantiomer. So while observed rotations can change because of path length, because of C, at constant temperature in a sodium D line, specific rotation is a constant for a specific enantiomer. Okay. The other point to note that's very important is, just like opposite hands are exactly opposite, enantiomers, pairs, enantiomeric pairs, that is two enantiomers, enantiomeric pairs, that is your two enantiomers, rotate light the same amount but in opposite directions. So now it becomes important that we give some sign for direction. Okay, so They rotate light the same amount, but in opposite directions. So we need to symbolize direction. And so if you rotate to the right, light to the right, so maybe I should create a space here. We'll just erase some of this. So if I observed a rotation of light to the right, so if we knew we started with an oscillation in this, and I measured the emerging beam and the rotation was now to the right, so we've rotated this way to the right, clockwise, then that is a positive number. However, if the rotation was to the left, so that the final beam emerged this way, and was rotation to the left, it rotates the same amount but opposite direction, we would give that a negative value. So rotations to the left are given negative values for in degrees, and rotations to the right are given positive values. Now, let me ask you one last question. If different enantiomers, or enantiomeric pairs, the two enantiomers, rotate lights the same amount but in opposite directions, how much would an equal mixture of both enantiomers in solution rotate light? So we fill our sample tube with a 50-50 mixture of both enantiomers. If they rotate light the same amount but in opposite directions, they're going to cancel each other. If you said there'd be zero rotation, you're absolutely correct. Equal mixtures of enantiomers render the solution optically inactive. There is no optical rotation. So these mixtures of solutions that do not rotate light are optically inactive. Okay. Well, this is an excellent point at which to stop. We'll be pressing on and looking at this optical activity in a little more detail. And then we're going to have to come up with a methodology for naming these enantiomers and distinguishing between them in nomenclature. So, this is Dr. Brian Lloyd Scribblecast. I thank you for listening.